Hi, I'm Nick Salvatore with Pacific Defense Solutions, and in collaboration with the Air Force Research Laboratory, today we'd like to introduce you to our work on learned event-based visual perception for improved space object detection. To set the stage for our work, our ultimate goal is to improve the detection and identification of dim space objects. Recent developments have led to an explosion in the number of resident space objects in various Earth orbits. Of these RSOs, our primary interest is in satellites and space debris, both of which have apparent visual magnitudes far less than that of even the dimmest stars in the night sky. For those unfamiliar, apparent visual magnitude is a reverse log scale of object luminosity, and the dimmest objects visible with the naked eye are around positive 6 to 7 MV, whereas the RSOs we aim to detect can be as low as positive 15 MV. In addition to the low luminosity of these objects, we also have to contend with the significant photon noise in CCD imaging sensors, and from a computer vision standpoint, the lack of distinctive features that might separate a satellite from any star in the night sky. Finally, there's a lot of interest in the space community in being able to detect these RSOs in daylight and cislunar scenarios, which can be really difficult given how much dramatically brighter the ambient conditions can be compared to the objects we're trying to detect. Given the challenges we're facing in our task, one of the potential solutions we explore in this work is the use of dynamic vision sensors. Now, dynamic vision sensors are a relatively new type of sensor that generates an asynchronous response to pixel-wise changes in intensity, i.e. events, rather than a conventional image frame. This behavior enables them to have very high dynamic range that is ideal for detecting minute differences in luminance, and they ultimately have an extremely high sampling rate with a relatively low data rate compared to conventional sensors. As an added bonus, they have very low power consumption, which makes them ideal for embedded platforms, and perhaps most importantly, some previous work has already shown them to be effective in detecting stars in daylight. In order to facilitate experimentation and supplement model training, we've developed an event-based simulator that produces randomly generated space scenes using elements sampled from real-world data collections. We start with using the SatSim space simulator, established in previous work to generate space scenes with low sim-to-real gap, to generate sequences of raw photoelectron counts emulating an ordinary data collection. Having raw photoelectron counts provided gives us an advantage over event-based simulations in other domains, since we're able to directly emulate the behavior of the dynamic vision pixels to produce realistic one-dimensional event streams that we can then operate on directly or integrate over time to produce conventional images. At the bottom of this slide, you can see an example of a real event-based satellite collection on the left-hand side, and on the right we have an equivalent simulated sample, which was generated using this pipeline and known sensor parameters and scene conditions. To accomplish the task of localizing these dim targets, we opted for an ensemble YOLO network that fuses features extracted from an integrated event image and from 3D point cloud representation of the same event-based data. We leveraged previous work in this domain by including an image feature extraction backbone previously used with CCD satellite collections. For point cloud feature extraction, we trained and compared the results of different versions using PointNet, PointNet++, and PointConv. Just as an aside, in preliminary work we did try to use point cloud models alone, but found that models had great difficulty distinguishing stars from satellites. On this slide we have some of the precision and recall results for each of our model configurations, comparing a purely frame-based model in blue to the ensemble models with each of the point cloud architectures. Detection results were analyzed on simulated and real datasets, and then performance of simulator-trained models on real datasets was analyzed both with and without intermediate transfer learning. Unfortunately for our analysis, we had a very limited set of real data collections, and not all relevant sensor parameters were available, so there is a very apparent sim-to-real performance gap in the detection results. Nonetheless, we see that the inclusion of point cloud models in the ensemble framework shows improved performance in nearly all scenarios. In addition to the customary precision recall analysis, we also analyzed detection performance with respect to each of the sensor parameters and scene conditions. Going into some of the key takeaways we found from this analysis was that field of view had the largest impact on model recall, which can be expected since larger field of view results in more ambient light striking the sensor but no additional signal events. We also found that the recall saw a sharp drop-off once target magnitude fell below positive 16 MV. Probably the most surprising result we saw here was that recall actually began to fall as target velocity increased past a certain point. Here are our full detection results for each of the testing groups. As we saw in the PR curves, the model including PointNet++ performed the best on simulated datasets, whereas the original PointNet model performs best by far on real data, though this gap in performance narrows when PointNet++ is pre-trained on simulated data. While our results have shown that the ensemble network has greatly improved detection performance for our task, one of the most critical issues moving forward is collection of a much larger real-world dataset, with full sensor parameter and scene conditions recorded. This would not only improve our model performance, but also allow us to further assess the accuracy of our simulation and help guide future improvements. Naturally, we would also like to explore new detection models that can better natively exploit event-based data, and are also looking into methods of performing real-time contrast threshold adjustments to maximize target EBSNR. Thank you for your time.